Hi, welcome back to another session of physics made easy. In today's lesson, we shall learn Newton's third law of motion. So let's quickly move to see what Newton's third law of motion states. As you can see, Newton's third law of motion states to every action there is an equal and opposite reaction, and the action and reaction acts on two separate bodies. So let's understand what does this mean. So a force acting on a body is always the result of its interaction with another body. Let's take few examples. Suppose you kick a football. So this kick launches the ball on its trajectory because you exert a force on the ball. At the same time, you feel the force that the ball exerts on your feet. Similarly, in case when you pull a sofa, the sofa moves forward because you exert a force on the sofa, but at the same time you feel the pain of pulling the sofa because the sofa in turn exerts a force on your hand. So in each of these cases, the force that you exert on the body is opposite in direction to the force that the body exerts on you. And experiments have shown that whenever two bodies interact, the two forces that they exert on each other are always equal in magnitude and opposite in direction. This is precisely what is Newton's third law of motion. So here action and reaction are either of the two forces. So in case of sofa, the pull on the sofa, you may call it as the action, then the reaction becomes the force exerted by the sofa on your hands. So in nature we see all the forces acts in pairs. So if there is an action, there must be a reaction. So let's take a puzzle. I mean, you can call it a fallacy. It says that I pull a book. The book pulls me. Why should the book move at all? So I mean, let's analyze this problem or situation, whatever you may call it. So here we have the book. So I pull the book with a force F. So I have drawn the forces which are acting during this situation. So the force F acts on the book. Now since by Newton's third law the book will pull the hand back, so there will be another force F acting on the hand. So if you see what are the forces acting on the book, only the force F which is on the left hand side. So due to this force the book moves towards the left, and you feel the pulling of feel to pull the book because there's another force F which acts on the right hand side and which acts on your hand. As you can see, the book would have not moved at all had there been two forces as shown in the second figure, one in this left direction and the right direction, with same magnitude and same line of action acted on the book. But this is not the case, so the book moves towards the left. I mean, now once we understood Newton's third law of motion, let's move to what do we mean by conservation of momentum. So Newton's third law of motion in fact has given rise to this very important principle called conservation of momentum. To understand this, I mean, let us assume we have an isolated system. Isolated system means there are no external forces acting on the body, on this system. So in this we have an isolated system comprising of two particles as shown in the figure, particle A and particle B. So let's assume that these two particles interact with each other. When I say interact, I mean let's say they collide with each other. So due to this collision, of course there will be a force. So let's assume there will be a force acting on particle A and particle B also, and by Newton's third law we know that these two forces will be equal in magnitude but opposite in direction. This negative sign shows the direction factor. So we have this, so which translates into this, that is the vector sum of these two forces are 0. So if we assume Pa and Pb are the momentum of the two particles A and B, we come across this. So in other words, the we have the rate of change of total rate of change of momentum equal to 0. Hence that when I say the rate of change of momentum is 0, that means the momentum is not changing with respect to time. That is, the total momentum p, which is the individual momentum of the two particles, is constant, it's not changing. So from this we see, for any isolated system, the total momentum of the system is always constant. So the law of conservation of momentum states that if the vector sum of external forces on a system is 0, the total momentum of the system is constant. This is a very important law which we will use in our analysis further down. Hope you have enjoyed today's lesson. Please feel free to send your feedback in the address learnphysics1232@gmail.com. Thank you.